do a little bit of genetics, because this is an inherited disease. Basically, different alleles produce different beta globin proteins. And there are some rules. And of course, there are some exceptions. Because this is biology. But these rules will get you a long way. Number one, at the protein level, it is codominance. That is, both proteins are made. You got two alleles, you make two kinds of protein if they're different. The alleles act independently to give the phenotype. And number three, roughly speaking, doing something is dominant to not doing something, right? So I want to apply those rules to the following situation, right? To this hemoglobin Christchurch situation, as a way to think about what they mean, because they apply in general. So we could make our allele table. I want to add beta globin produced, and then contribution to phenotype. Because today we get to explain why things are dominant. So I don't want to give away which is dominant, which is recessive, because I want you guys to think about it, so I'm going to use sort of generic symbols here that don't give that away. Normal, where number 71 is phenylalanine, is that we'll call it the big H allele, and that has the normal phenotype. We'll call H big C Christchurch, where number 71 equals serine, and all 145 others are the same. And this has hemolytic anemia. One of the things that's important to think about what's going on here is how amazingly sensitive biological things can be to little changes. You remember, hemoglobin is 4,400 atoms, 4,000 atoms. You change a small number of them, phenylalanine to serine is a dozen atoms difference out of several thousand, is enough to make the protein non-functional and give you a very serious disease. Right? So it's a pretty sensitive system here. Okay? So every other amino acid, in hemoglobin Christchurch, every single other amino acid is exactly the same. The pizza is exactly the same except that you put pepperoni instead of mushrooms on it. Right? And it causes you this serious problem. I guess if you're allergic to meat, that could be like that. So what I want to do, I'm deliberately leaving out dominant and recessive because we're going to figure that one out piece by piece. Genotype, beta globin produced, and phenotype. Right? And so there are the usual three genotypes: big H, big HC, big HC, and then the really important one, big HC. All right. As I said above, in that rule way up there, at the protein level, it's codominant. So both alleles always do their thing. Right? In the case of a big H person, you get 50% of your protein from the big H allele, and the other 50% from the other big H allele. So that gives you 100% normal hemoglobin. All right? In HCHC, what's the protein going to be? So the HC allele is going to make 50%, and is that going to be normal or Christchurch? Christchurch. The other allele is going to make 50% normal or Christchurch. So what do you got? 100% Christchurch. Right? So this guy's 100% Christchurch. And the phenotype of this is normal. All right. And the phenotype of 100% this is hemolytic anemia. What I want you to do now is talk to your neighbor. I want to know, in this person who's likely to be the patient, although I don't know, we have to figure out whether he's likely to be the patient now that I think about it. In that individual, a heterozygote, what protein or proteins are you going to find following those rules? So what proteins are produced, and what's your best guess as to that person's phenotype if they're heterozygous for this? Right? Think about it. Talk to your neighbor. I'm going to call on somebody.